Hello everyone, welcome to the second lecture of the chemistry of dilute solutions, the colligative property, and today's subtopic is relative lowering of vapor pressure. In order to understand relative lowering of vapor pressure, we have to take a pure solvent and enclose that solvent with the help of a bell jar. This is the surface of that pure solvent, where only the molecules of the pure solvent are present, and some particles or some molecules are coming out of the solvent. These are the particles, these are in the vapor phase, and these molecules are responsible for the partial vapor pressure of that pure solvent, which is P10. Now if you dissolve some solute in that solvent in order to make a solution, then the appearance of the surface would become a little bit different from the previous one. Look here, some sides of the surface become occupied by the solid molecules which are non-volatile. So this time the vapor molecules produced are coming out from a lesser surface area, because some part of the surface area are occupied by the solid molecules. So that is why this vapor pressure, this partial vapor pressure, becomes lesser than the previous one. So as a result, if this one is P1, then P10 is greater than P1, or vice versa, P1 is less than P10. So this is the physical explanation how the vapor pressure gets decreased due to dissolution of some solute within a liquid. If we try to find out the thermodynamic explanation, then if mu is the chemical potential of the solvent within a solution, mu0 is the chemical potential of the pure solvent, and x1 is the mole fraction of the solvent within the solution, then the chemical potential of the solvent within the solution, mu equals to mu0 plus RT ln x1. So x1 is less than 1, that is why mu is less than mu0. So chemical potential decreases. Now the relationship between chemical potential and pressure is what? That is d mu dp, or conversely it is dg dp, that is the rate of change in free energy with respect to pressure, and this is nothing but volume plus v. So from that we can conclude that pressure and chemical potential are directly proportional to each other. So if pressure decreases, then chemical potential also decreases, or vice versa. That means here the chemical potential has decreased, as a result the pressure also has decreased. So this is the phenomena which is known as the lowering of vapor pressure. Now let us calculate. So vapor pressure of the pure solvent is P1. The vapor pressure of the solvent within the solution is the vapor pressure of the pure solvent is P10, and the vapor pressure of the solvent within the solution is P1. So P1 is less than P10. So what is lowering of vapor pressure? The lowering of vapor pressure is the difference of these two, and it is denoted as delta P. So delta P is equals to P10 minus P1. Now what is relative lowering of vapor pressure? This is actually the colligative property, the relative lowering of vapor pressure. So the vapor pressure difference per unit pressure, that means this parameter has now to be divided by P10, and that is delta P by P10. So this relative lowering of vapor pressure is delta P by P10, and this is nothing but P10 minus P1 by P10, or 1 minus P1 by P10. Okay, so this is about relative lowering of vapor pressure. Now move on to the Raoults law for a non-electrolytic, non-volatile solute, and that law is P1 equals to x1 into P10, so that x1 is the mole fraction of the solvent, x2 is the mole fraction of the solution, P1 is the vapor pressure of the solvent within the solution, P10 is the vapor pressure of the pure solvent. And if x2 is the mole fraction of the solute, then x1 is nothing but 1 minus x2. So P1 is equal to 1 minus x2 into P1 0. Okay, and if we rearrange this equation, then we get the relationship x2 into P1 0 minus P1 0 minus P1, and x2 equal to P1 0 minus P1 by P1 0. Okay, now look at this graph. Here, this is the graph of the pure solvent, which is actually increasing with increase in temperature. But the same graph, if you plot in case of a solution, it will be always placed below that graph of the pure solvent. It will go parallelly, but it will always be placed below this graph of the pure solvent. Suppose at this point, if this is the temperature, the arbitrarily taken this temperature, at that temperature, if the vapor pressure, partial vapor pressure of the pure solvent is P10, then that of the solvent within the solution is P1. So it is found from the graph clearly that P10 is greater than P1. Now x2, the mole fraction of the solute, is actually N2 by N1 plus N2. But since this is the chemistry of dilute solution, so N1 is very much greater than N2, because the very small amount of the solute is dissolved. It is mentioned here, for a dilute solution, N1 is very much greater than N2, or N2 is very much less than N1. As a result, N1 plus N2 can be written as N1. N1 plus N2 is almost equal to N1. So in place of N1 plus N2, we are writing here N1. So this is x2 equals to N2 by N1. This is almost equal to. Now the further expression of N is W by M, where W is the mass and M is the molar mass. So for the solute it is W2 by M2, and for the solvent it is W1 by M1. And the rearranged form is W2 capital M1 by W1 capital M2. Okay. Therefore, the relative lowering of vapor pressure delta P by P10, which is actually, we have found here, this is x2. Look, this is actually x2. x2 equals to P10 minus P1 by P10. It is actually obtained from the Raoults law. Okay, so x2 is the relative lowering of vapor pressure, and this is equal to, as we have found here, W2 M1 by W1 M2. So M2 is this. After having rearranged this equation, this is P10 by P10 minus P1 into W2 by W1 M2 into M1. So here, if all these parameters are known, then the molar mass of an unknown substance can be measured by using the lowering of vapor pressure phenomena. So by measuring the relative lowering of vapor pressure, the molar mass of an unknown substance can be determined. So that's all for today. Thank you. Have a nice day.